So we've been talking about sensation, but now we're going to move on to perception, which is the method by which sensations experienced at any given moment are interpreted and organized into some meaningful fashion. One thing that happens, though, is that we have a perceptual constancy. So sometimes sensory stimulation appears to change even when the objects we're sensing stays the same. You have a remarkable ability to recognize that the object remains unchanged even though it may look, sound, or otherwise seem different. This is a perceptual constancy. Your brain's ability to maintain the same perception of an object even when conditions around it cause it to produce different sensations. So here's an example of shape of constancy. Objects change in your eyes constantly as we or they move, but we're able to maintain a content perception, shape constancy, size constancy, and brightness constancy. For example, imagine you're playing kickball and you're deep in the outfield. A powerful kicker sends a high pop-up your way. When it first leaves the kicker's foot, that red rubber ball looks minuscule from your spot in the field. But as it soars towards you, however, the ball seems to get bigger and bigger until your whole field of vision is nearly filled with the red ball when it reaches to you. According to your eye, that ball actually got bigger, but your brain converts that changing sensation into a constant perception. Your brain knows that red rubber ball is the same size, whether it's far away or in your arms. There's actually auditory examples of perceptual constancy. Consider the sound of your friend's voice as you walk from one campus building to another. Specifically, imagine that the two of you start in a small classroom with a low ceiling, then walk outside into the open air, and then enter a large atrium with a high ceiling. The sound of your friend's voice strikes your ear differently in each of these three settings because of the different acoustics. Louder in the small room, quieter in the open air, and with more echo in the atrium. But it never crosses your mind that your friend's voice changed. You perceive it as constant even though the conditions caused the sensation of your friend's voice to create change. Let's continue on with constancy. So here is shape constancy. It's hard to tell if the figure on the upper right, if you were just to look at that by itself, is it a trapezoid or a square that slanted backwards? If we add texture to it, though, that texture gradient helps us see that it's actually a square and that it's tilted backwards. There is a concept called Gestalt, which means an organized whole. So a Gestalt is the tendency to integrate pieces of information into meaningful wholes. This line of thinking was actually created in the 1900s in Germany, and it maintained our sensations are processed according to consistent perceptual rules that result in meaningful whole perceptions, or gestalts. One such gestalt are figure-ground relationships, which are the tendency to perceive objects or figures as existing on a background. So this figure ground, as you can see, you have a perception that these are people going downstairs. Now, this is also known as a reversible figure, which visual illusions which the figure ground can be reversed. You can either see the people going down the stairs or you see the arrows going up and down. Other ways that we use Gestalt grouping principles are through proximity, similarity, continuity, closure, connectedness, and common regions. Grouping is the perceptual tendency to organize stimuli into coherent groups. So here are those reversible figures again. which is the visual illusions which the figure and ground can be reversed. So in this picture, do you see faces or do you see vases? Look at it carefully. I've known people who can never see the faces. They only see the vases. But if you are looking carefully, this would be a forehead of a person, their nose, their lip, their open mouth. They look like they're laughing. That comes down to a chin, and it comes down. You have the same chin on this side. It goes up to the nose right here and up. Each one of these has a different face with a different expression being given. We often group by proximity, so grouping nearby figures together. We also group figures that are similar to each other. So in this case, it might be by color. This is a fun one. We use closure to fill in the gaps. Can you see the triangle? However, there is no triangle. You have only used closure to create one. Or here, the rectangle. But again, there is no rectangle. This is one of my favorites, the sphere, and then the Loch Ness Monster. It looks like there's a surface that the Loch Ness Monster is going under. However, there isn't. You have just used closure. Continuity, the perceived continuous patterns. The law of continuity says lines are seen as following the smoothest path. So if you were to choose the smoothest path, believe it or not, you would go with this one versus this, because this seems like a smoother. It's the top branch is seen as continuing the first segment of the line. Contiguity is another Gestalt principle. Tendency to perceive two things that happen close together in time as being related. An example of this. Years ago, there was a really cold snap in Denver, Colorado, where everything was shut down. The roads, the highways, and it was all shut down for about 3 or 4 days. It was very cold. There was a lot of snow. And 9 months later, guess what? There was a baby boom in Denver, Colorado. Now, the question is, does cold weather create babies? No. In fact, if that's what you think, I'm going to have to send you over to health class. However, we put it together that, you know what, when there are blackouts, there is more procreation that tends to take place. This is called a Necker cube, and it's just kind of a fun trick of the mind, if you want to say that, or a trick of the eyes. It is not clear which pattern should be predominant. Are you looking inside the box, or are you looking down into the box? Depth perception is another tool we use to understanding perception or organization of perception. The ability to perceive three-dimensional space and accurately judge distance. We use depth cues to do that. So there was a woman by the name of Eleanor Gibson, and she did an experiment called the visual cliff experiment. And what she found was that if you're old enough to crawl, you're old enough to see depth. We see depth by using two cues that researchers put in two categories: monocular cues and binocular cues. Here's just a quick lesson on her visual cliff. As you can see, there's a table, and on this side there is a piece of plexiglass. Underneath is the same material that the baby is on, and so from the baby's perspective, it looks like there is a cliff. They have the mother in this experiment go on each side of this table and coax the baby to come to them. What they found is most of the time the baby will not cross this line because, again, they have depth perception, that they think that there's a cliff there. Binocular cues we use retinal disparity. So really quickly, I want you to put your two fingers together like this gentleman right here, away from your eyes, and about 5 inches directly in front of your eyes. And as you bring it towards yourself, you will see a finger sausage, kind of like this, okay? What is happening is your eyes are working together as you bring those fingers closer to you. They come together and to focus. This is called convergence. Neuromuscular cues. So when two eyes move forward or inward toward the nose to see near objects, they also then will move away from the nose to see far away objects. Monocular cues, however, you really only need one eye to use these. We use several different cues to give us an idea of monocular cue, to give us this idea of distance with monocular cues. You use linear perspective, interposition, relative size, texture gradient, and shadowing. So relative size, if two objects are similar in size, we perceive that the one that casts the smaller retinal image to be farther away. We also use that texture gradient, so the indistinct fine texture signals an increasing distance, where the larger texture makes us believe that it's closer, so the balls are coming out towards us. We also use relative motion, so objects closer to a fixation point move faster in an opposing direction to those that are farther away from a fixation point, moving slower and in the same direction. This is the Muller-Lyer illusion. So this illusion provides a great example in understanding how perception is organized. Studying faulty perception is as important as studying other perceptual phenomena. So here's the question. Which line is longer? AB or BC? Well, if you guessed BC, I hate to tell you this, but you are wrong. The longer line is actually AB. Oops, let me explain that one a little bit more. So the reason why, and it is an illusion, that's why they call it that, is because remember that contiguity or continuity? When the line of least resistance would be this, right? So this is how your eye wants to follow this line, which gives us the illusion that this BC is longer. However, it is not. Okay, which one is coming in? Which dots are in and which dots are out? Now, most of you will tell me that the top row is coming out and the second row is going in. Do you know what you're basing your decision on? Usually it's shadows and light. So from this perspective, the light is coming from this direction, coming from this direction, and it is casting a shadow on this side. Because it's casting a shadow, this would be up. But let's say, for just a second, the light was coming from this direction. Then it would be just the opposite. This would be in, and these would be out. Motion perception also is used. Objects traveling towards us grow in size, and those moving away from us shrink in size. The same is true when the observer moves to or from an object. So relationships between perceived size and depths. To perceive the size of objects accurately, we must also perceive their distance accurately. Thus, many visual illusions occur simply because a particular image lacks sufficient depth cues. I can remember sitting as maybe a first or second grader in like a school forum, and they were talking about lies and the difference between big lies and little white lies. And the teacher had two hearts up by her. She had a white heart and a black heart. And she made the white heart look small because it was supposed to be the little white lie. However, at the end of it, she put the two hearts together, and they were the exact same size. And they were trying to, of course, teach us that little white lies were just as bad as big lies, and that we shouldn't lie. But I'm telling you, that was many, many years ago that I sat under that lesson, and I still can remember it so clearly, because that visual illusion, I remember just going, how did they make that happen? Well, really, it was about visual perception. She was holding that white heart closer to her while she held the black heart further forward. And so it made it look like that white heart was smaller based on the depth cues. Here's an interesting room. If you've ever been to the mystery spot in Santa Cruz, I believe it's kind of like this. Both girls in this room are of similar height. However, we perceive them to be different heights as they stand in two corners of the room. Now, one reason is because the developers of this room, and by the way, this is called an Ames Room, the developers of this room have really done a great job in making up for any depth cues that we might be looking for, like sizes of the squares on the floor. We might be looking at sizes of the windows or the clocks. This is how this room's actually built. As you can see, it goes up actually on one side and forward. So therefore, she appears to be much larger in this corner than the girl back in this corner. We also look for color constancy. So perceiving familiar objects as having consistent color even when changing illumination filters the light reflected by the object. So I'm going to change the filter here. You still believe that that apple is green. Those apples are green, right? No matter what filter we put on it. Okay. Let's talk about the moon illusion. The moon just above the horizon typically appears to be unusually large because we perceive it as unusually far away from ourselves. This is a result of distance cues, which makes the horizon moon seem farther away. The horizon moon appears to shrink in size if it is viewed through a narrow tube that eliminates the perception of distance cues. This illustrates the importance of context effects. We also can adapt in our perception. So we actually have the visual ability to adjust an artificially displaced visual field or prism glasses. So the glasses as this gentleman has on is making it look or making everything seem to be in front of him, but in actuality, it's off to the side. However, if he were to continue to wear those glasses, his brain would adapt and it would get things back to normal. I was in a classroom once where we used these glasses and had to play catch with each other. I'll just tell you right now, the balls were going all over the place instead of to the person we were supposed to throw it to. But again, if we would have continued on, our brain would correct for that, and we would end up perceiving the distance and the direction correctly until we took off the glasses, and then our brain would have to have some time to readjust again. Okay, that is it for perception. I know this has been a lot this week, but hopefully you got something out of it. Make sure you read your chapter, and we'll see you next week.